Okay, so this is part two. This is going to be predicting covalent compounds. So if you were given some nonmetals that were going to react with each other, um, this would be a way to predict it. So we're going to go back a little bit to those Lewis dot structures to try to figure out how this will happen. And then from there, we're going to also look at names of covalent compounds and how to write the formulas from there. Okay. So if we go back and think about valence electrons, because that's what we use for the Lewis dot structures, and you use your periodic table, hopefully you'll remember that. Oops, sorry. There's 4 on carbon and 7 on chlorine. Excuse me. So the way that would look is carbon has its 4 and chlorine is hanging out with its 7. And so if you remember covalent compounds, co meaning to share, valent, those valence electrons. So they share those valence electrons to create a bond. So what's going to happen is because these substances aren't going to live by themselves in nature, it's not like there's one carbon and one chlorine going to, just happen to bump into each other and react. That's not how it works. There's a whole lot of carbons and a whole lot of chlorines. So basically what's going to happen is stuff's going to keep adding on until you have full octets, those full outer shells of electrons, in order to create a stable substance. All right, so the sharing of electrons can happen in this way. So they're going to share these electrons so that chlorine now is using carbon's 1, right? And then the other 7 from chlorine, and so that equals 8. But like I said, it's not just going to be one chlorine coming in here. So there's going to be another one, and there it is. They're going to share those 2, one from chlorine and one from carbon. And so another chlorine can come in here, and they're going to share those 2. 1, 2, 3, 4, 5, 6. And then another one can come in here, and they can share those. So if you look at this, sorry, I'm on the other screen. You've got 1, 2, 3, 4, 5, 6, 7, 8 for carbon, and then each chlorine also has 8. And so what that's going to look like, you typically write the one with a lower electron negativity first. So if carbon is a lower electronegativity, if you need a refresher on electronegativity, our electronegativity trend is it increases up and to the right. So the stuff that's over here on the top right, like fluorine, that's got the highest electronegativity. Okay. I hate the way that keeps popping up. Okay, so for this formula right here, we've got 1 carbon, so we've got 1 carbon, okay, and then we've got 1, 2, 3, 4 chlorines. So our 4 chlorines are going to come in here, and that's what our formula will look like. Okay? And we do the same thing for everything else, okay? So if we're looking at hydrogen, remember that's one of our exceptions for the octet rule. It's a duet rule, so it only wants 2 electrons in its outer shell, okay? So it's going to have the 1, and then it's got the 1, and then we've got oxygen hanging out here, and it's got 6. 1, 2, 3, 4, 5, 6, okay? And so those hydrogens are going to come in. One hydrogen can come in and contribute. And so now this hydrogen has 2, this hydrogen has 2, and this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It's got 2 bonding regions because it's bonded to 2 other atoms here. And then it has these what are called lone pairs, okay? So those are lone pairs of electrons. And lone pairs of electrons actually, what is going on? Take up a whole bunch of space. Okay, they take up a whole lot more room than bonded pairs. And so if you remember from the molecular geometry lab, or if you haven't done that yet, those those lone pairs are going to push everything else out because they're like, and so water would have a bent shape, so it would look like that. Okay. But if we think about that formula, that's 2 H's and an O. All right, so nitrogen. Nitrogen is one of our diatomic molecules. So when it exists in nature by itself, it has to exist in a pair. It does not exist as just in. Okay, so diatomic meaning two atoms of nitrogen. So nitrogen is going to come in here, and it's got 5 valence electrons. 2, 3, 4, 5. Just write it like that. Okay, and our other nitrogen is going to come in here, and it's got 5. Okay. Well, we can't just add electrons, or we can't add like a nitrogen here and have these sharing, and then another nitrogen here, because they would be sharing. Okay, so what we have to do is we have to think about how to rearrange all those so that they're sharing, and they need to be able to share 6 electrons. Okay, because they've got 2 in their outer shell already that are not going to bond to anything, but they've got 3 that are going to share with another 3. Okay, so think of it that way. And so what's going to happen is those nitrogens are going to put their lone pair on the outside, and then they're going to create what's called a triple bond. So now there's 1, 2, 3, 4, 5, 6, 7, 8. And so this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. And so that's how diatomic nitrogen exists. That's what it looks like. And so for bromine, look at your periodic table, it's got 7 valence electrons. Okay, and so bromine, and I'm just going to write it to make it easy in life. And so it's got 7 and 7, and so all they need to do is share 1 each. So share 2. So now this bromine over here has 1, 2, 3, 4, 5, 6, 7, 8. And this one over here has 1, 2, 3, 4, 5, 6, 7, 8. So that BR2. So our next one is from names. Basically what you're doing is you are looking for the elements that are in here, and you're adding the prefixes as subscripts. Okay, so if we find xenon on our periodic table, fluoride on our periodic table, it's going to look like this. So xenon and fluoride. Okay, but xenon doesn't have a prefix. Fluoride does, and it is a hexa, which hexagon. That's the only thing I can think of with hexa, but that means 6. So our formula is XeF6. Here we have carbon. There's no prefix, so there's only one, carbon. And then hydride is just hydrogen. And how many hydrogens are there? Tetra, think of tetris. Okay, so 4, CH4. Sulfur, and oxygen. How many oxygens? It's a di. So I'm just going to pop a 2 right there. We don't have to worry about things like parentheses for these, okay? Because we're not, we don't have to think about ratios or anything like that. Carbon monoxide, so carbon and oxygen, and mono meaning 1. So that is the formula for carbon monoxide, 1 carbon, 1 oxygen. And then if we come down here, we've got phosphorus tetraoxide. So phosphorus and oxygen. And so how many phosphoruses are there? There's 2. And tetra meaning 4, so there's 4 oxygens. I hope that helps everybody. Let me know if you need anything else.